So just going to go over, I know this slide says it's a review, maybe you've never heard these probability topics before, but it's probability stuff that computer science students would want to know. So it'll come up in a discrete math class. So, so maybe we'll just start right off with some examples. So suppose we have an example, let x be the outcome of rolling a dice. The probability mass function of rolling a dice would be the probability of each of the possible numbers, 1 through 6, would be 1/6 for all the numbers, for all the integers between 1 and 6. And the probability of any other integer would be 0. You couldn't roll a dice and get some other number. So this produces a probability distribution function that says the probability of getting a 1 is 1/6, the probability of getting a 2 is 1/6. And we could code this up in computer science. If the integer is between 1 and 6, output 1/6, any other number we would output is 0. So we could simulate a roll of a dice. So you could have questions about probability. We could say something like, where we could use the data on the last slide, we could say for a roll of a dice, what is the probability that the outcome will be a 2? So the answer is, since this is a discrete case, only integer outcomes, we can read it directly from the probability distribution function. Probability of being a 2 would be 1/6. Suppose we had other styles of questions would be like from negative infinity up to a number, or from a number off to positive infinity. We could say like, what is the probability the outcome will be 2 or less? So we'd have to go from negative infinity and go all the way up to 2. And the only possible outcomes will be 1 or 2 in that case. So it would be, there's a 1/6 chance of a 1 and a 1/6 chance of a 2. So it's 2 out of 6 would be the chance of getting a 2 or less. Okay, then there's the idea of what is an expected value for an event. So an expected value means if you were to roll it on average, what would you expect to come out? And the way we'll calculate that is to sum up the probability of the event occurring times the value of the event. And again, a lot of these are probably easy to follow with an example. So the expected value of the outcome of a roll of the dice would be, well, the value could be a 1 and there's a 1/6 chance of that happening. Or it could be a 2 and there's a 1/6 chance of that happening. 3, 1/6, and so on. And we'd add this all up and the average would come out to 3.5, right? Now, we're not saying if you were to roll a dice, you would expect it to land on 3.5. Actually, it'll never land on 3.5 because there is no 3.5. But whatever it comes out to be, the median, not the median, the expected value would be 3.5. So, it's important to know it doesn't have to actually be a possible outcome. Then there's the idea of we want to have some kind of a statistical way of saying how much does this event vary from the expected value. So there's the idea of what's called a variance of a random variable. And it's basically an index that you look at that number and you go, oh wow, if the number's really high, you say this thing's going to vary a lot. If the number's low, then it won't vary too much. And it's defined as the variance of a random variable is if you were to take an average, an outcome, and subtract that from the expected value, how far would you, so this represents how far away an individual event is from the average. So for example, if you rolled a dice and a 2 came out, this value in here would be 2 minus 3.5. 3.5 is the average. So we would calculate the expected value. That would be 3.5. And then you rolled a 2, so you'd be 1.5. This value would be 1.5, and then we would square it. So by squaring it, we'd get rid of a negative sign, right? It could be negative if we're below the average, and it could be positive if we're above the average. And we square it. So that eliminates the negative sign. And it just comes out, it's a number that we can look at. If it's very large, you say, wow, this thing varies a lot. If it's very low, it doesn't vary too much. And if you take this and you just work it through, work through your trigonometry, you get x squared minus 2 mu x plus mu squared. And just work your way down. You'll eventually convince yourself that the variance of x, which is sometimes written as sigma squared, the notation for sigma squared, ends up being whatever the expected value of the outcome you get, if you square that, figure out what is the expected value of that, and then subtract it from the expected value squared. So let me just go, hopefully there's an example. Oh, okay. So one more thing, and then before we go over an example. The square root of the variance, which is, we use the Greek letter sigma to denote that, would be the standard deviation of a random variable. And the standard deviation of a random variable is how far, a measure of how far you'd expect to be from the expected value. So let's just take a look at an example. Suppose, and I kind of went out of my way to just have interesting variances. Suppose you had a random variable that comes out of 50 every time. I can't think of it something, let's say we had a coin that had 50 written on both sides, and you flip the coin. Every time it comes out 50, right? So what would the expected value of a flip be? You'd say there's a 100% chance it's going to be a 50, so it would be 50, right? So the expected value would be 50. Now, if we wanted to calculate the variance, the question is, what do you expect the outcome to be squared? You expect a 50, and squaring that is 2,500. And if you subtracted that from the expected value squared, you get 2,500. So, well, it'll make a little more sense in the next example. So the variance in this case would be 0. And that's an index, right? We said the variance will always be a positive number because you take the expected distance from the average and square it. So it gets rid of the negative sign. So 0 means this thing will not vary at all. Every event that comes out will be exactly equal to the expected value in every case. So standard deviation of 0 means that the random variable is likely to be within a distance of 0 from the expected outcome. So now suppose we had a random variable that half the time comes out 40 and half the time it comes out 60. So again, what would be the expected value? It would be a half times 40 plus a half times 60, which is 50. We have an expected value of 50. Actually, it'll never come out 50, but the expected value is 50. So the variance would be, we would take 50% of the time. So the variance would be the square of the expected value. So we would have half the time, not the square, multiplying it by itself. So half the time it would be 40 squared, which is 1,600, and half the time it would be 60 squared, which is 3,600. So we would take an average of that, and that would give us, so in this case, this value, what is the expected value of x squared? We would take 40 squared and 60 squared and take an average of them. And then subtract that from the expected value, which is
2 squared.
Which is 50 squared. This one would be 50 squared, and this one would be 1,600 plus 3,600 divided by 2 squared. So we would end up with, maybe I should have cleaned this up, but this number here is 2,600 minus 2,500. And that being the case leaves us with 100. So we're making a statement, the variance is 100. So that tells us, all right, it's more than 0, so the results vary from the mean. They're somewhere, you know, some of them are more than it, some of them are less than it. And it's kind of an index to tell us. And if we were to take the square root of it and we say one standard deviation is 10, that means, standard deviation of 10 means the random variable is likely to come out within 10 of the expected value. More likely than not. Okay. And another example, kind of the same idea, but just more extreme, would be, suppose you had an event that half the time comes out 0 and half the time it comes out 100. Once again, the average is 50. So the expected value is 50. But this number is going to be even larger. Now, half the time it comes out 0 and half the time the square is 10,000. Right, 100 squared is 10,000. So this ends up being 5,000 minus the expected value squared, which is again 2,500. We have a variance of 25,000. If you take the square root of it, your standard deviation is 50. So this number is much higher, meaning that this random variable has the same average, but the results are much further from the expected value. So there's the variance and therefore its square root, the standard deviation, is just like an index that gives you an idea of how much it's varying from the norm. Okay. So if we wanted to calculate, like for the roll of the dice, what is the variance of a roll of the dice? Well, the expected value, we did this before, is 1, 2, 3, 4, 5, 6 divided by a 6, so the expected value is 3.5. Now, if we wanted to calculate what is the expected value of the roll, if you took every roll of a dice times the probability that it come out and square the numbers, that would be, so the numbers 1 through 6 squared would be 1, 4, 9, 16, 25, 36. So if you took this number, the expected value of the outcome, if you took the outcomes and squared them, what would you expect that to come out to? That comes out to 15.17. And the expected value of 3.5 squared comes to 12.25. And you subtract one from the other, you get 2.97 is the variance of a roll of the dice. And if you took the square root of that, it comes to 1.71. So it is more likely, we're saying it's more likely that the roll of the dice will be within 1.71 distance from the average.
Which is 3.5.
Right, so you will be within, plus or minus 1.71, you'll be more likely to be within there. So it just kind of gives us a feel for how much these events vary from the average. So that's what standard deviation and variance measure. Okay, so we could, look, like with the dice, we have to look at it and look at what the possible outcomes are. Maybe roll the dice several times to make sure they all have a 1/6 chance of happening. And then there are some questions that come up in life where there's some famous discrete case distributions. There's the idea of the uniform distribution. Well, I'll go through an example of each one of these. The uniform distribution, the geometric distribution, the binomial, and then the Poisson distribution. So, and they kind of come up in math and computer science a lot. So suppose we had a coin that had a 60% chance of coming up heads. So there's really something wrong with the coin, right? It's not a 50-50 coin. 60% chance of coming up heads. Therefore, it has a 40% chance of coming up tails. And you were to ask a question like, if you were to roll this coin over and over and over until you get your first heads, what would the probability be that you would get the first heads on, let's say, the 4th roll? So you would use the formula for what's called the geometric distribution. The probability of it being any number n would be the probability of the event occurring times the probability the event didn't occur for all the other times, right? So for example, what would have to happen for the first time a heads comes up to be on the 4th roll? We'd have to have tails, 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 heads. It's the only way it can happen, right? So what's the probability of getting a tails on the first roll, times the probability of getting a tails on the second roll, times the probability on the third roll, and then times the probability of getting a heads on the 4th roll. So it might be good if they took this P and put it over here, so it looks like you got tails, 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 and then finally a heads, but they put the P here. So it would be a 40% chance times a 40% chance times a 40% chance, and then finally times 160% chance for the heads. So it would be tails, 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 followed by heads.
Okay.
And like I say, since since it's happening in this order, it might have been good to put the 0.6 here to show like it's tails, 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 finally by heads, but it's really the same thing with the P on either side. Okay. Then another common question could come up with, was anyone a Mets or Phillies fan? Peter? No?
Mets.
Mets? Oh, okay, all right, so I figured we're between New York and Philadelphia, so let's say the Mets have, every time the Mets play the Phillies, the Mets have a 55% chance of winning the game, whether in New York or in Philadelphia. And this season they're actually playing 19 times this season, which I thought was a strange number. But if they're playing 19 times and you want to know what is the probability that out of those 19 times, the Mets will win some fixed number like 15 out of 19. So you want to make a bet that they'll win at least 15. You want to know what's the probability they'll win exactly 15. You could use this formula, which is very similar to the last one. We're basically saying, if you take away this part, we're basically saying there's going to be this many wins and this many losses. So if you were to take this part away, that would kind of be like answering the question, what is the probability they would win the first 15 games and then lose the remaining 19 minus 15, the remaining 4 games? So that would be in a particular order. That would be, what's the probability of winning 15 in a row, then losing 4? But then if you remember from our combinatorics, this notation means 19 factorial divided by 15 factorial divided by 4 factorial, which means of all the permutations we could do, this would be the number of permutations of this combination. So it's really like doing it in 2 parts. You're saying, what is the probability that I'll get my 15 wins followed by my 4 losses, and then say, now take those set of outcomes and try every unique permutation of it. And then that'll show you how many different ways that that could be over the 19 games, that there would be 15 wins for the Mets. So the value n is the total number of games played. The value I is the number that you're trying to figure out what is the probability of that coming out. So then it's the probability of the event happening times k times. Yeah, let me change this. This should be k. And this should be k. Okay. Okay, sorry about that. So, I want this event to happen k times, so it would be the Mets getting 15 wins and the Phillies getting 4 wins. And so that would be 19 factorial divided by 15 factorial divided by 4 factorial, which would be kind of like picking 15 from 19. And then, right, so that's just kind of the breakout of it. And so it's 55% raised to the 15 and 45% raised to the 4. So again, this would be the probability of having the Mets win the first 15 and the Phillies win the last 4. And then taking, so let's say you wrote out a string of 19 letters, MMM 15 times and PPP 4 times. Then say how many different unique permutations are there in this many.
Yeah, so on the bottom where it says 15 factorial minus 4 factorial?
No, times.
Times.
That's
okay.
a star, yeah. So, right, whenever this notation from our combinatorics, it would be you're picking this many from that set.
Okay.
And so now the question is, how many permutations are there? So it's like those questions where you have like 19 balls in an urn. They always use balls in an urn in these questions. But you have 19 balls in an urn and 15 are orange and 4 are maroon. And you want to pick, what's the chance of getting 15, picking 15 out?
Okay.
So you would arrange them all from all the 19 different ways, but then of the 15, they could all be combinations of each other. So you'd be dividing out. So there's 19 factorial ways of arranging them,
Yes.
but 15 out of 19 are repeats of each other. So you'd be dividing by 15 factorial, and then the other 4 are repeats of each other and divided by 4 factorial. Okay. So yeah, so it's just basically, this is, you know, the probability, you would put in a number and this spits out what the chance is. And you'd have to put in every combination. So this would be every combination. K can range from 0 through 19. Any other value it should, actually there should probably be a comment here that says if K is negative or greater than N, but the output should be 0. Okay, so the uniform distribution, we've seen this before with a dice. This is just basically every possible outcome has the same exact probability. So in the discrete case, if you have, like for a dice, the numbers can range anywhere from B being 6, the highest number, and A being the smallest number. So 1 divided by 6 minus 1 less than the smallest number would be 1/6. So for example, for a dice, if you want to know what's the probability that a 5 comes up, the probability distribution would be the highest number minus the lowest number, then also minus 1 in the discrete case. We wouldn't have the minus 1 if it was the continuous case. So each one of those values between A and B, including A and B, would be 1/6. So if you want to know what's the probability of the outcome of a dice, and all the events that are possible all have the same exact probability, like a dice, you would just divide it by 1 divided by the number of possible outcomes. And they all have the same probability. Okay, so another random variable. This one's kind of interesting. How this was developed is a little interesting. So it's named after famous French mathematician Poisson. Have you guys, any of you guys speak French? By chance? No? Have you ever gone to a restaurant and there's a section of the menu that says Poisson on it? No? Okay, so Poisson I think means fish in French. But it's a person's last name, so it's not the fish random variable. Some person named Poisson. And anyway, this could be used, the discrete case version of this could be used to solve questions like, let's say in a hockey game, let's say it's observed that there's 3.5 goals on average in a hockey game. And you want to know, there's a game going on tonight, what is the probability that there will be 6 goals scored tonight? If you know that on average there's 3.5 scored. So we can use the Poisson formula. You just say, what is the probability we'll have 6 tonight? And the formula basically says, take the average, raise that to the number you're looking for, and then take the number E, which is Euler's constant, raise that to the average, and then divide that by the score you're looking for, factorial. So 3.5 is the average raised to the 6th, the number of goals we're trying to figure out what's the probability of now, times e to the minus average divided by the number of goals we're looking for, factorial. So we can figure out what is the odds that there'll be a 0, a 1, a 2, and this would obviously go off to infinity. When you get up near infinity, this should come out very, very close to 0. Not a very good chance there'll be 100 goals when the average is 3.5, but it does go off to infinity. So the curve kind of looks like it kind of bubbles up to around 3 and then it goes off to infinity with a slight chance of happening for the higher scores. Okay. And then there's the idea, really last thing we'll talk about is the idea of a conditional probability. And this would be when you have an event that's going to occur, and its outcome could be affected by some other event that has occurred. So we call this a conditional probability that says, what is the probability distribution that E will be a certain value, given that F has already come out at a certain value? Okay, so an example might be, if you were to roll 2 dice, well first let's just look at, if we were to roll 2 dice, what is the probability distribution for the total of the 2 dice? So if you roll 2 dice, each one having numbers 1 through 6, the only possible outcomes, the lowest possible outcome is 2, and the highest possible outcome is 12, right? And if you think about it, the probability of getting a 2, you would have to get a 1 on the first dice and a 1 on the second dice. So sometimes it'll help you, it doesn't change the probability. If you think of the dice as having 2 colors, one is red and one is green. So what is the probability of getting a 2? The red dice has to come up a 1, and the green dice has to come up a 1. And the chance that the red one comes up a 1 is 1 out of 6. And then you also have to have the green one come up 1 out of 6. So you'd say 1/6 times 1/6 is 1 out of 36. Then you thought, what's the probability of getting a 3? Well, there's 2 ways we could get a 3. The red dice could be a 1, and the green dice could be a 2.
Or vice versa.
Or, yeah, the red dice is a 2 and the green dice is a 1. So there's 2 out of 36. So out of the 6 dice, there's really 36 different things that can happen. So a 3 is more likely than a 2 because there's 2 ways for it to happen. 2 out of 36 ways. And then for a 4, there's 3 different ways. A 3 and a 1,
3 and
a
1.
1 and a 3, and a 2 and a 2. Right? So there's 3 out of 36. And as you get closer and closer to 7, it gets more likely, then it starts going back down again. Kind of a symmetrical thing for dice. So this would be like a list out, we're writing it out as a chart, the probability distribution for numbers, the output of numbers of the total of 2 dice. So if you don't know what either dice was, this is what they would come out to. Now suppose you were given a piece of information about these 2 dice, like you know the result of one of them. So what if we said that one of them, what if you told one of them came out to be a 3? Okay, so yeah, so you're being asked the question, you have a red dice and a green dice, and you're rolling them, and you're saying, what's the probability distribution for the outcome? So if you don't know anything about either outcome, it's this, right, what we talked about before. But if I now tell you, well, the green dice came out of 3, I don't know what the red dice is, but the green dice came out of 3, then I'm really asking you, what is the probability distribution for the total, given that the green one is a 3? That would actually change things, right? Because now it's impossible to get a total of 2 if one of them's a 3. It's possible to get a total of 3 if one of them's a 3, because the other one has to be at least 1 through 6. You can't get anything 10 or higher, because one of them's a 3, it can only go as high as 9. And now these become 1/6 each, all the numbers in between. There's a 1/6 chance of a 4, 5, 6, 7, they all have 1/6 chance, once you're told that the green one came out of 3. So this is the conditional probability. So it's the probability distribution for the total, given the condition that the green one came out 3. And then you kind of have to be careful, how much does the conditional information change your answer? So for example, suppose you have a deck of cards, and you're selecting a card from a normal 52, standard 52 playing card deck. What is the probability of picking out an ace? So there's 52 cards, 4 of them are aces, right? So that would be 4 out of 52, which is 1 out of 13. Right? 4 out of 52 is the chance you'll pick out an ace. Suppose somebody has removed one of the jacks from the deck. Would that then change the probability of picking out an ace?
Yes.
And in that case, yeah, because you've removed one non-ace. So it would be 4 out of 51. That would be the new one. So you could say what the probability of picking an ace out of a deck of cards, given the condition that a jack has already been removed, would now be 4 out of 51. So all combinations of picking any other card. So picking a king would be 4 out of 51. And then picking a jack would be 3 out of 51. So it changed all the probabilities, just that one piece of information. Then sometimes there's information that kind of looks like it's conditional, but it actually doesn't change your answer. So what is the probability of picking an ace, given that somebody has removed one of the spades from the deck? So if I said you have 52 cards, and somebody came along, removed a card, and I could tell you, well, it was a spade. Now what is the chance you're going to pick out an ace of the remaining 51 cards?
What happens if it was the ace of spades?
So that's the thing, if it was the ace of spades, right, so the thing is, out of the 13 cards that are spades, the probability the one you pick is an ace is exactly the probability of picking it, so it actually won't affect the outcome. It'll still be 1 out of 13.
Okay.
Even at, like, so for example, if you removed all the spades, now you have 39 cards, it would be 3 out of 39, which is also 1 out of 13. But even removing a card and just being told the information that it was a spade doesn't change the outcome of what's the probability of picking a spade.
Oh, okay. You're picking a spade, not an ace. Okay.
Right, it's just saying it removed the spade from the deck. So now you have 51 cards, and all you know is one of the spades is missing.
So it'd still be 4 out of 51, right?
Well, no, I guess I'm just throwing this in to say, be careful that the information you're being given actually alters the probability of what you're trying to figure out. This is a case where it wouldn't alter.
Okay.
So yeah, you'd have to be given information that makes the probability of an ace coming out something different than 4 out of 52.
Okay.
So for example, like, I'll give you some examples of some useless information. Suppose I said you have a deck of 52 cards, then I randomly take 20 and throw them out, now you have 32 cards. What's the probability of picking an ace? It's not 4 out of 32, unless I told you the cards I threw out have no aces. But if I just say I just threw out 20 cards, it's still 4 out of 52. The ones you threw away still have to be considered. So even though an ace was removed from the deck, it may or may not, even though a spade was removed from the deck, it may or may not have been an ace, and the probability it was an ace is exactly the same as the original answer.
Okay.
So it doesn't affect the outcome. Right, so it's just a matter of like being, careful that the conditional information you're being given, you can actually tell how much it alters the probability distribution. So, so where you would have this is the distribution for the total of 2 dice, then you give an information that says, well, one of the dice was a 3. Now what does the total look like? That actually impacts the total. Suppose I told you the green dice came out even. I don't tell you what number it is, but I just say it's an even number. Then what would this become?
First one would be nothing.
Right. Yeah, so this will kind of make an interesting question. So we know this is either a 2, a 4, or a 6. So the outcome can't be 2.
It can be that.
1/6, although it could be a 2, a 4, or a 6. The chance that it's a 2 is 1/3, and then the chance that the other one is a 1 would be 1/6. So it'll be a 3rd times a 6. It'll be 1 out of 18. It's a 3, right? Because there's a 1/3 chance the green dice was a 2. It could be a 2, a 4, or a 6. 1/3 chance it was a 2, and then a 1/6 chance the other dice would be a 1. So this would be a 1 out of 18. This would be 0. This would be 1 out of 18. The only way to get a 4 would be the green one was a 2 and the next one was a 2. So this would also be 1 out of 18. To get a 5, there's 2 ways.
2.
A 2 and a 3 and a 4 and a 1. So that would be twice as likely. So that would be like 1/9. Right. So, but basically it alters it. So really what we're doing is you're taking the probability of the not knowing the outcome of this conditional property, calculating what that is, and then saying, with this new information, does this alter my distribution? And if it alters it, fill out how it alters. If not, like removing a spade doesn't alter the chance of getting an ace, then it would just stay the same. Okay. So yeah, like I was saying, this is, for a discrete math class, we're looking at probability from a discrete case, so we're always looking at integers. A continuous case, you could say like, what is the probability of getting a 7 or less? So we'd be going from really negative infinity and adding up everything all the way up to 7. And then that would be the probability of getting 7 or less, which would be 4 out of 6 in this case. And if there were continuous time questions, like if you said, a bus is going to show up at a bus stop uniformly distributed between 2 o'clock and 3 o'clock, meaning every piece of time has an equal opportunity of being hit, like it's being randomly showing up between that time. You couldn't ask a question like, what's the probability it will show up at exactly 2:30, because that's an instant in time, as opposed to 2:30 and 1/10 of a second is a different instant in time. So you could only ask questions, what's the probability of showing up between 2 and 2:30? That you can answer, or 2 and 2:15. You could do ranges like that. But discrete case probability is just we're looking at outcomes being integer values. Okay.